Okay, friends, we have been so far dealing with binary system and simple eutectic system where A and B, the two binary components, they do not mix in the solid, but they mix in the melt. This we essentially started from this expression which I derived, XA liquid divided by XA solid is equal to delta HM by R into 1 by Tm minus 1 by T. That was our expression of the cryoscopic equation. And for here you can see XAS, and this XAS we considered equal to 1. That means whatever solid phases we had, they were pure. Now, we do not do this. We also take in what happens to the phase relations if XAS also has a value not equal to 1. And you know mole fraction will have a value which is negative. Either 1 or negative. So now we look at the equation once again. If we take, we all know from our crystallization sequence that we studied, T is less than Tm, where Tm is the melting temperature of the pure phase and T is the temperature of the equilibrium, which is lower than the melting temperature of the pure phase. Now, if we take again, Tm is equal to T in this scenario where XAS is not equal to 1. That means it's not equal to 1. Previously we took it as equal to 1. So for Tm is equal to T, this expression T minus Tm by T into Tm, this turns out to be 0. And so the right hand term turns out to be 0. Oh, I forgot. Ln of this. So if we take T is equal to Tm and this whole term becomes equal to 0, then we come to this relationship XA in the liquid divided by XA in the solid is equal to 1. Or XA liquid is equal to XA solid. This is what we come to. That means if we take T is equal to Tm, then XA is in the liquid is equal to XA in the solid. So now if you look at the binary diagram that we did, it is essentially both of them have the same composition. This can be done only if both of them have the same composition or equal to 1. There is no other possibility by which this can work. But if we take it slightly differently, that T is less than Tm, then this term is negative. If this term is negative, then e to the power negative term, and so the ratio of it will not be equal to 1. Therefore, at a particular temperature, XAS and XAL, XAM will not be equal to 1. That means they will have a different composition. So if we draw a binary diagram where we take A and B and we take TMA and this one as TMB, this is what it was. Then if you take a particular temperature T here and we draw an isotherm, then XA solid and XA liquid they will not be the same. They will be different. So it will be something like XAS and XA liquid. If we happen to change the T value to another value, then obviously this ratio will also change. And similarly, if we have another T, this ratio will change. And if we draw, so what will happen eventually to the phase diagram? If we do this, then eventually we will land up with this type of an expression, this type of a diagram. A, B, T, temperature, A, temperature, B. And you will end up into some sort of a figure which is like that. Have you understood? So if you take a particular temperature here, then this is the composition of the solid and this is the composition of the liquid. Remember, here XA is equal to 1.0 from here where it is 0. So at any particular temperature, you will have 2 points. If you change the temperature, you will also have 2 points, and this is how the phase diagram will look like. Now in this diagram, this is liquid and this is AB solid solution. Do you remember in the last diagrams that we talked about, we called it pure A and pure B. But here at this point I am saying AB solid solution. That means A and B are not pure phases anymore, but A and B form a solid solution, like I have talked to you before these sets of lectures. I talked to you about solid solutions. And this part of the diagram, you will have AB solid solution plus L. So this is what you get from the phase diagram. And this line as always is the liquidus, and this is called the solidus. So we have what is called the liquid. Above this temperature we have, which is the liquidus. The temperatures above this you have just liquid, and this is the solidus. At temperatures below this you have only solids, AB solid solution. And between the solidus and the liquidus you have a solid solution, AB solid solution, in equilibrium with the liquid. So this is how the phase diagram in general looks. Normally what happens, one of the components, it can take more complex shapes, but we don't go into that at the moment. You can see you will have A and B, where one of the components will have a higher melting temperature than the other component. So this will be more refractory in this diagram as drawn. A is more refractory in nature. Refractory means it is of a higher temperature than B. So now in this lecture we will talk about how crystallization and melting occurs in this rock, involving a melt, which is a liquid solution of A and B, and a solid, which is a solid solution of A and B, and you have an intervening zone separating the liquidus and the solidus, where the two minerals and the liquid are in equilibrium. So we try and read all this diagram. So now here you see the important part played by XA solid solution. This XA is now a variable. In the last eutectic crystallization, A was not a variable. AX in solid was not a variable. Only XA in the liquid was a variable. Here, XA solid and XA liquid are both variable. Okay, having said this, let's draw a diagram and let's get going. Remember, this is the solidus and this is the liquidus. Sorry, the higher temperature one is the liquidus and this is the solidus. Here you have AB solid solution. Here you have the liquid, and here you have AB solid solution plus liquid in equilibrium. And first we will talk about crystallization from a melt. Okay then. So let's take a melt of this composition. Let's take a melt of this composition. Maybe we shift the melt a little bit here. This composition. So if this is so, then let's say this is 50, this is 25, and this is 75, and this is XA, and this is 100 weight percent. So there is not a problem here. If you write this is weight percent, then it's fine. You can also write XA, and then it would be 1 and 0. So this is, let's say, weight percent. So now, if we take a melt at this composition, so the composition of the melt at this point of time is initial composition, and we write this as L0, and with L0 the composition is A75 and B25. This is the composition of the initial melt. Now, if we now cool down L0, this is a melt where A molecules are present, A and B molecules or components or phase components of the melt are present in the ratio 75A and 25A. And if you start cooling it, so obviously the temperature goes down along this isoplet and reaches this point. So this point is, let's say, L1, and at this point is what is called the liquidus. So at this point, this field is AB solid solution plus liquid. So what happens, the moment you're on the liquidus, you should be precipitating because of the demands, because the liquid is in solid solution in AB solid solution. So if this is the liquid, then this liquid intersects this at this particular temperature. At this particular temperature. So if this is L1, then this is S1, and the temperature is T1. So at this temperature T1, when the liquid composition reaches T1, that means it lies on the liquidus. Immediately, the requirement has to be fulfilled that the liquid has to be in equilibrium with the solid. And how do I find out? I take a line at this temperature, say this is T1, at this temperature I draw a line, and this point here, this point, this then is the composition of the first composition. So corresponding to L1, you produce a liquid which is S1, and that S1 then has the composition of A95 possibly and B05. Now remember, this is not a mixture of A95 and B5. No, it's not a mixture of pure A and pure B. Here you have a mineral AB in which the component A is 95% and the component B is 5%. This makes up the mineral AB, solid solution. Now once this happens, where you have a liquid in equilibrium with the solid solution, so this solid will precipitate and this will have a composition of A95 B0Y. As this solid is crystallized, obviously the melt has to move once, because you see the solid has more A than the liquid. So once you crystallize this solid, then the liquid composition becomes impoverished in A. So the liquid becomes enriched or richer in B. So the liquid composition moves in this direction, but at the same time you have cooling. So this is also the direction. So effectively what happens, the liquid composition moves along this direction, along the liquid dust, and yet you have an equilibrium between the crystallized solid and the melt. So what you have is here a new composition L2 at a temperature T2. You have a liquid composition now L2 and at the temperature T2, and this line intersects this solidus, and this gives you the composition. This one was S1, this one was S2. And what is S2? S2 is A90 B10. Now you can ask me, what is this? Now, you must understand that S1 solid, which was here, and which was in equilibrium with L1, which had this composition. Now the liquid composition has moved to L2, which is at temperature T2, and at this temperature, if you draw a line, this intersects the solidus curve here, and you produce S2. That means the solid S1 has now been converted to solid S2. Solid S1 has been converted to solid S2, meaning one thing at least, that the composition of the mineral has changed. Previously, if you remember, the composition, when we are discussing eutectic, the composition of the mineral was always fixed and it was pure. Here, the composition of the mineral changes. Here, the composition of the mineral changes. That is very important. That means what? If you have a crystal that is crystallizing, and outside you have a melt, and this forms a particular system, then there is constant interactions between the crystal and the melt. There is constant interaction between the crystal and the melt. There is constant element transfer between the crystal and the melt. And you can well understand that as this crystal forms, here for example, it changes from S1 to S2, the composition of the mineral, if it has to change, then the melt composition with which S2 is in equilibrium has also got to change. Because it's a closed system and nothing comes in, nothing goes out. Right? So, in this type of a diagram, the most important difference is the crystal and the melt always exchanges matter across crystal melt boundaries. So, and another thing is happening here. If I write this also, if this point is S2 and this one as L2 as I have written, and if I write this one as L0 here, then you can see this divides the fraction into two parts. One is S2 L0 and the other one is L2 L0. Can you see this? S2 L0 and L2 L0. Now going as we have gone before, if I write this as M and if I write this as N, then M divided by M plus N. M divided by M plus N, this should give you the fraction of the melt. Have you understood? The fraction of the melt. And this part, L0, L2, divided by, or this factor, N, divided by M plus N, this is the fraction of the solid. So, here you can see, at this point, there is, say for example, if you see L1, S1, you see at L1, S1, this N here is equal to 0. N is equal to 0. So if N is equal to 0, then this equation is M divided by M plus N. So M divided by M plus N will be equal to 1. That means the fraction of melt is equal to 1. That means the whole thing is a melt. And this S1 is like a small embryo of a crystal. Right? So now what we see, from going from L1 to L2, two things have happened. One is the fraction of solid has increased, because you see the fraction of solid N, the length of N has increased. So the fraction of solid has increased, and at the same time the composition of the solid has also changed. So two things have changed. The composition of the mineral, or the composition of the rock has changed, as well as the proportion of the crystal melt ratio. This has also changed, and you have much more fraction of the rock. Have you understood? So this is how crystallization continues. So you can imagine another point. This will be T3, this will be, you can S3, and you can draw the point, this will be S3, and now this will be L3. So you can see, here you can find out the composition of S3, here you can find out the composition of S3 from this axis, and here you can find out the composition of L3. The L3 and the S3 compositions are different. That is why in the equation that I showed you, ln XA liquid by ln XA solid was a decimal. So they are not same, they are not identical. And ln to the power was negative, and therefore ln to the power of was not the same, it was not 1. So now what we have, so now what is M now? M now is this, and this is M. Can you see? This is now M. You can see you started from M with N almost equal to 0 here, and now as crystallization has progressed, N has become larger and larger and larger, and M has become smaller. And you can see M divided by M plus N, which is the fraction of the liquid, that is becoming less, and N divided by M plus N, which is the fraction of the solid, that has been increasing. And at the same time, the solid composition itself, the mineral composition itself is changing, as is changing the composition of the liquid. Now, when will this event stop? When will this event stop? the event will stop. As you can see, if this is the fraction of melt, then m will become equal to 0. Where will m will become equal to 0? When this S3 point will reach here. Can you see this? This is where you will have L4, and this is where you will have S4, and this is the point where it was L0. So when the melt composition, the composition of the solid along the solidus coincides with the initial composition, therefore, and this will be the new composition of the melt. This will be the new composition of the melt. That means here, say, L4 will be equal to A25, B75, and S4, let us see, S4, or the reverse, it's very nice. So it's A75, B25. So, A75 and B25. This will be the last solid to which is in equilibrium with this composition. And the first solid, S4, will be equal in composition to the initial liquid for equilibrium crystallization. So this is essentially what will happen. As you move down, therefore, as you crystallize, therefore the solid composition moves from S1 to S4. This is what the solid composition moves. And the liquid composition moves from here to here. Important part to discuss here is the liquid composition was initially here, and then it moved towards this. That means, to start with, the liquid composition was richer in the higher temperature component to start with, but ended up being lower. Similarly, if you take the solid, it started with very enriched components, enriched in A temperature, but through interaction with the melt, the crystal composition continuously changed till it reached the same composition as the initial melt when the last drop of liquid has exhausted. You see here, at this point here, your n is almost equal to 0. There is no n because the fraction of liquid is almost gone. Because the whole is now, this is now, totally is now n. So your last fraction of the liquid is gone. This is how crystallization happens in a solid solution phase. There are many facets to this, but we will discuss this on a different context. We will not discuss this now. First, let us concentrate on equilibrium crystallization. First, we discussed equilibrium crystallization of a simple binary eutectic system involving pure solids. Then we are discussing a binary system using impure solids and impure melts. So we are still now left with trying to find out what happens on melting, equilibrium melting, and we should be aware that it should be a process that is reverse of the crystallization process. So I will erase this and draw it again and see what happens. So now we discuss melting of a binary where it has a mineral so obviously if it's melting, then you have to start with a rock which is melting, and the rock has a mineral which can change its composition. It's capable of changing its composition. In eutectic crystallization, there was no such thing as the solid can change its own, as the minerals A and B could change its composition. Although, if the in the eutectic crystallization, if A and B individually remained pure, but a mixture of them would of course change the composition of the solid. But the composition of the minerals itself would not change. So, let's take a rock which R0, and let's say this is A50 and B50. So, this is the composition of the rock, and I draw a line like this. This is the rock composition, R0. Now, if I ask myself a question and answer it, the first is, if I heat the rock, when will the melting occur? When will the rock start melting? The answer to that question is, as you heat the rock, the temperature of the rock increases till it reaches the solidus. Till the temperature of the rock coincides with the solidus. Have you understood? So let's say this temperature is T1. At this temperature, when we heat the rock, this temperature is the temperature of the solidus. Remember, the temperature of the solidus changes as a function of the composition. The temperature of the solidus changes as a function of the composition. If I take a different rock here, for example, you can see here, if I take a rock, melting would be initiated at a lower temperature. Have you understood? If I take a rock which is more enriched in the refractory element, more enriched in A, then the melting temperature would be different. So, the temperature at which a rock would melt depends on the composition of the rock. It would not, but this is a major difference from the simple eutectic system. If you remember, in the simple eutectic system, no matter what you hit, the first melting temperature remains the same. Remember, it's the eutectic temperature. But here, there is no eutectic temperature. If you melt a mineral, the melting would be initiated at a temperature depending upon the composition of A and B in the mineral. But in eutectic system, the proportion of A and B does not dictate the temperature of melting at low degrees of melting. Remember, there it was always the eutectic temperature, no matter what proportion of A and B you took. So long A and B was there, the melting temperature was fixed. But major differences are here, where you will see this is not valid if you have mineral composition. So I will erase this at the moment. And so, for example, at temperature T1, this will be the composition of the solid. What would be the composition of the liquid? Very clear. You just join it. So this will be the composition of the first liquid that forms. And this will be the composition of the first solid. This will be the composition of the first solid that is in equilibrium with the liquid 1 at the temperature T1. What I tried to say before is, if you chose another composition, you would still form S1L1, but they would be at a different isothermal condition, at a higher temperature, if the phase had higher amounts of A. Now what will happen here, as you see, as S1 undergoes melting, you produce a melt, which is L1. Now the L1 is enriched in B. The S1 L1 is enriched in B. So your S1 becomes enriched in A. So if you melt S1 to L1, then the S composition will become S2 at temperature T2, and then your liquid composition will be L2. Do you understand that? So if you have a solid S1 and you melt it to L1, L1 is richer in B, so S1 solid has to become richer in A, and so the S1 solid changes its composition to S2. If it's S2, at that particular temperature, S2 should be in equilibrium with a liquid L2 at another temperature. S2 cannot be in equilibrium with L1 because L1 is stable only at a different temperature. So if S1 composition changes to S2, then at S2 you draw an isotherm and it should intersect the liquid as at L2. And this should be your new composition of the melt. The initial composition was L1. And now you see this. I write M and this is N. Or once again, let me write it the way. R0 L2 is equal to M, and R0 S2 is equal to N. So now, so what is M divided by M plus N? So this is M divided by M plus N. So this will be the fraction of the liquid or solid. It would be the fraction. You see, if there is N here, it should be the fraction of the solid, right? And N divided by M plus N, this would be the fraction of liquid. Now you see, at T1, N was 0. At T1, at S1, N was 0. That means the fraction of liquid was 0, obviously, because there was hardly any melt when the first melt was generated. So this will go on, is the reverse process of equilibrium crystallization. And as more S go into melting, so you would have S3 here, and you draw an isotherm parallel to this, and you will have at this point L3. And now you see here, this will be the new composition of L3. This was the composition of L2. This was the composition of L1. And this was the composition of S1. This is the composition of S2. And this is the composition of S3. So this is, you can see here, L3, L2, L1. And this is S1, S2, S3. So you see, from L1 to L3 and S1 through S3, the whole material is becoming more richer in A. And you can see at this point, this is now where your N is. This is N. Can you see? Now the fraction of N is increasing. Have you understood? So here at S1, N was 0. This was N1. Now it's N3. So N1, N2, N3. And so you can now say what will be, what should be the temperature at which the last solid will go into melt. Which is the temperature at which the last solid will go into the melt. So if you say the last solid, then M by m plus n, this should be equal to 0. The last solid. The last solid means there is the fraction of solid is equal to 0. So m now should become equal to 0. If this is so, then here is the point. This is the point now. Do you see this? This is the point now. This is where you can see your m, which was this, reducing, and here m is equal to 0. So whole of it is now liquid, and this occurred at this temperature, which is say T4. This is your solid S4, and this is your liquid L4. Now you see here, S4, this is your composition S4, and this is your composition L4. So the last composition of the melt L4 is the same as the initial composition of the solid from which you started. It is obvious, it's a closed system. So when it is solid, it's R0. When it's fully liquid, it's L4. L4 and R4 has to be the same. Otherwise, it cannot be a closed system situation. It cannot be a closed system situation. So the important point to note here is there are certain important points apart from this. You see, as the melting occurred, you see I'm drawing this black line. This is how melting occurred, and this is how the solid composition changed, and this is how the liquid composition changed. This is how the liquid composition changed over a time interval. Have you understood? So now there is an important problem here which I must tell you, and you remember this. Remember, in the simple eutectic system, when we were melting for, for low degrees of melting, the more heat you gave, you produced more melting. So there was thermal buffering. The temperature did not rise. The temperature was buffered. What happened as you gave heat, that was transferred into latent tutor fusion and materials were passed into melt. But the temperature did not change. So that caused thermal buffering. Here, there is no thermal buffering. No thermal buffering. And you see, S1 has a lower melting temperature than S4. So if you have to go on melting this to get from a pure rock to a pure melt, you have to go, if you want to go on melting, you have to supply heat to the system. There is not going to be any thermal buffering if you involve such a system, binary system. It is very, very important to realize that when you're melting solid solutions, minerals which are called solid solutions, then the temperature needs to be continuously increased so that the rock is completely transferred to a melt. There is no question of thermal buffering, which was there during eutectic melting involving solid phases. This does not happen here. Why I'm saying this, that these are the differences between binary eutectic melting involving pure minerals and binary melting involving impure minerals. Impure mineral melting, as you melt the mineral, the low temperature fraction is taken into the melt and the mineral becomes more refractory. That means it becomes enriched in the higher melting temperature component. So if you have to melt the next stage, then you have to heat it. a little bit more. If you stop the heating, melting will stop. It will not be possible for the rock to melt anymore, because compared to S1, the mineral S2 has a higher melting temperature. So you have to go on supplying constantly more and more heat for the rock to undergo melting. You have to continuously do it. So there are major differences in melting, major differences in equatorial crystallization and crystal involving pure phases and those involving impure phases. Okay, I think I will stop here. So we will move over to some other topics later. Yeah, thank you for the moment.